I've mentioned before, Kirchhoff's current law, voltage law, Ohm's law, that's all you need. But this week we're going to look at systematic ways of applying that for more complex circuits. So we've given you a circuit, resistors, sources in it, and said, you know, find this voltage. You've done it in quizzes, done it in mid-semester tests, equivalent resistance and so on. But if I gave you a much more complicated circuit and said, find these voltages and currents, you might think, I'm not sure if, you know, I can't guarantee that I can do that. It might require some inspiration. But it doesn't. And that's what we'll see this week. If you systematically apply Kirchhoff's current law at every node of the circuit, you can solve for everything. If you systematically apply Kirchhoff's voltage law around loops in the circuit, you can solve for everything. And it's a technique that is very, very methodical. You can, in fact, get a computer to solve circuits in this way. So if you use Kirchhoff's current law at all the nodes, that's called nodal analysis. If you use Kirchhoff's voltage law around all the loops or meshes, it's called mesh analysis or loop analysis. And they're the techniques that we will look at this week. What does it build on? Well, as we said, we've looked at current, voltage, power, resistors, voltage sources, current sources, KVL, KCL, intelligent. In fact, we did that all in the first 2 weeks, and then you analyse circuits with op-amps in it, using Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law, and the golden rules of operational amplifiers for ideal operational amplifiers. So you've analysed circuits already. Just a reminder, there are your Kirchhoff's laws, and another reminder from one of the memes entered last year. Didn't win. So we've done all that. We need more advanced circuit analysis techniques. We'll look at nodal, loop, something else called superposition, and Thevenin and Norton equivalent circuits. That's the next 2 weeks, before we move into capacitors, inductors, and phasor analysis in the 2 weeks after that. So if this circuit's not particularly complicated, but I could certainly ask you to find V0 and I0 in this circuit. I don't know, take a minute, see if you can start working that out. What's V0? What's I0? How would you start it? Don't necessarily have to finish it, but what would you do? Okay, anyone think they might have a way to start it? Anyone want to? I've still got coffee vouchers left over. Anybody want to say? Oh, yep. Solve the current on the node at the bottom. Whereabouts? How would you do that? Sorry? Kirchhoff's current law at one of these nodes? The one on the bottom. So you might have, let's have a look. You could say down here, you could say there's a 2 amps, there's I0, I don't know what the current is there though. Well, that 4 and that current, but I don't know what that current is. So yeah, I mean, you're right. All you can do is apply Kirchhoff's current law or Kirchhoff's voltage law and use Ohm's law. You don't have any other choices. You've sort of just got to start. You know, you could do a KVL around a loop, or you could do a Kirchhoff. So that is really the only choice that you have. But what nodal analysis says is, well, let's do that systematically. Let's provide this systematic procedure. What you do is you call one of the nodes ground, and I'm going to call this node here ground. Here's a ground symbol, 0 volts. I'm just going to say that's my reference node. Pretend that that's at 0 volts. I'm going to then label all of the other nodes. I'm going to say this is a node, that's node 1. This is another node, and the only other node in the circuit, that's node 2. And those, I'm going to say the node voltages are V1 and V2, and that's with respect to ground. So if I measured the voltage between this one and this one, it would be V1 volts, and between this one, which is, again, that's ground, and this one up here, it would be V2. If I can find V1 and V2, because here's the aim of nodal analysis, I'm going to label those. I'm going to try and find V1 and V2 by using Kirchhoff's current laws, and then everything I'll be able to write down. Anything I want, I can get in terms of V1 and V2 reasonably easily. So your next task is, suppose I knew V1 and V2, or you knew V1 and V2, how do you write V0 and I0 in terms of V1 and V2? And that's a MELTS question that should be open in MELTS. So find V0 and I0 in terms of node voltages. These things called node voltages, V1 and V2. There shouldn't be a lot of calculations there. It should just be understanding what those node voltages mean. Is that open in MELTS? Yep. Okay. So can you write down V0 and I0 in terms of V1 and V2? Because I claim if you can find the voltage in every node in the circuit, you can find any other voltage and current that you want quite easily, given those node voltages. That's the claim. Then we'll worry about how you can go about finding V1 and V2 in this circuit. All right, well, we can see what's we've got going there. Switch back for a while. See if we can get up to 60 responses. How do I lock this? Lock. What did we get? Well, a lot of 65, that's good. They think I0 is V1 on 3K and V0 is V1 minus V2. And the other ones were kind of variations, but with just slight sign changes. So let's go back and have a look. Yeah, certainly if V1, this means the voltage across that resistor is V1 volts. But by the definition of node voltage, because it's the voltage with respect to ground, which is down here, so I0 is going to be, certainly is going to be V1 on 3K. The other thing is, what is V0? Well, it's going to be V1 minus V2. This is a plus here, a negative there, so V0 will be V1 minus V2. So if I can find V1 and V2, I can quickly get the things that I want. So let's see if we can find V1 and V2. And the way we're going to do it, I have to redraw my ground. That's voltage V1. That's voltage V2. I'm going to apply Kirchhoff's current law at node 1 and then Kirchhoff's current law at node 2. So Kirchhoff's current law at node 1, what does it tell me? I've got to add, what's that current there? And I don't want to write I0 because I want everything in terms of V1 and V2. I want to do Kirchhoff's current law, but in terms of these V1 and V2. They're the things I'm trying to find. So I write all my equations just in terms of V1 and V2. So we already worked out that current there. That was V1 on 3K plus, what's that current in terms of V1 and V2? V1 minus V2 on 6K. So it's V1 minus V2 divided by 6K. That must be that current there. V0, we said, was V1 minus V2, so you divide it by 6K and that will be the current in that direction. I haven't finished. I've still got that, which will be minus 2 milliamps. That equals 0. I can multiply through by 6K everywhere and get 2V1 plus V1 minus V2 multiplied through. So minus 12, the K and the milli cancel out, equals 0. So that is 3V1 minus V2 equals 12. Now, that's not enough. It's one equation in the two unknowns, V1 and V2. So I certainly can't tell you what V1 and V2 are yet. And I'm going to have to do a Kirchhoff's current law at the other node, at node 2. Two unknowns, you'd expect to have to do two Kirchhoff's current laws to be able to solve for it. So is that okay at that stage, how you do the idea of it? You do Kirchhoff's current law, but everything's going to be in terms of these node voltages. So again, I've got to put in my V1 and V2. Now it's Kirchhoff's current law at node 2. This one over here. That current, what's that current? V2 minus V1 on 6K now. Remember when I did that current over there, I had it going in that direction, and you told me it's V1 minus V2 on 6. Well, now it's the negative of it. V2 minus V1 on 6. Plus, what's that current there? V2 on 12 plus this one there, which is just plus 4 milliamps equals 0. So that was 12K. Multiply through by 12K everywhere, I get 2 times V2 minus V1 plus V2 plus 48 equals 0. Therefore, I get minus 2V1 plus 3V2 equals minus 48. There's a second equation in two unknowns. Are there any questions? Because really, if you get this, you really have got nodal analysis. There are a few little tricks that we'll see. How do we deal with voltage sources? How do we deal? But this is really the main idea. So you get those two equations. And let's see if you can remember how to solve two simultaneous equations. I had to come up with 3. Excuse me for 1 second. So let's go backwards. What are V1 and V2? No? Yep, all right. Is that locked? Unlock. There we go. See if you can work out V1 and V2. Just a bit of mental arithmetic for early in the morning. You'll be a lot faster than me. Use your calculator if you like. Use MATLAB if you wish. Oh, come on, you must love MATLAB. Surely. Got it there, going. You probably don't need to. It's only 2 by 2. You could certainly have to solve 2 equations in 2 unknowns in the exam, maybe 3 equations in 3 unknowns. Of course, you could write this in this way. And you can see that you need to do a 2 by 2 matrix inverse if you want to solve it that way. Or Gaussian elimination, whatever you like. All right, I think you'll have made a pretty good effort there. Look at that. A lot of people think minus 12 on 7 and minus 120 on 7. So let's lock that. I reckon that's right. I reckon the 65 out of 69 have it. So that's right. You can solve that. Minus V1 would be minus 12 on 7 and V2 would be minus 120 on 7. But that's nodal analysis. How do we tackle a circuit like this? It's not just one loop. It's not just 2 nodes. They were the easy circuits to analyse. It might have multiple current and voltage sources, dependent sources and so on. Well, we use node voltages as the variables. If we can find the node voltages, everything else is easy. We've demonstrated that already. We choose one node as a reference, usually the node with the most connections, but often we just choose the one on the bottom. Doesn't really matter, but choose one as the reference. We assume all voltages are positive with respect to ground. Well, we don't really do that. We just say what their voltages are V1, V2, V3. Could be positive or negative with respect to ground. Doesn't matter. And if we have n nodes in the circuit, one of them is going to be ground, and we're going to do Kirchhoff's current law at all the rest. So if there are n nodes, we'll do n minus 1 Kirchhoff current law equations, and we'll have n minus 1 equations in the n minus 1 node voltages. And we can solve those. Then we'll know everything we need to about the circuit. Of course, we know we love history. So this nodal analysis was actually named after a man called Norbert Nodal. And so really you should call it NODAL Analysis. Norbert Nodal was an Icelandic electrical engineer and physicist, and he invented nodal analysis after a strange dream involving elephants and strawberry jam. He was recently voted one of the 100 sexiest Icelanders of all time. So, nodal analysis named after Norbert Nodal. Not many people know that. So, you've got something up on almost everybody. Norbert Nodal. So the most straightforward one circuit to use is ones with current sources. Because we're doing Kirchhoff's current law, current sources are easy, right? You're adding up currents, summing currents at nodes. If you've just got independent current sources, it's kind of the most straightforward application of nodal analysis. In this circuit there are 3 nodes. We need 2 equations. We can use the bottom node as the reference. We still need to find V1 and V2. This is basically the structure that we had before. If I go to node 1, this one here, I can write, it's exactly the same topology as the circuit we just did, in fact. So I can write V1 on R1, that's that current, plus V1 minus V2 on R2, that's that current. I wanted that one, so it'll be minus IA equals 0. And you could simplify that or write it as something V1 plus something V2 equals something. Won't bother doing that bit. You could go to node 2 and write that current, V2 minus V1 on R2, plus that current, V2 on R3, plus that current, IB equals 0. 2 equations in 2 unknowns, solve it, and you're done. Are there any? Again, I've got vouchers for questions. Good time to ask it. Resolve any issues. Some people get worried that I've sort of said, you know, I've got this current in one equation and this current in the other. Of course, one should be the negative of the other. Well, one's that term and one's that term, and they are indeed negatives of each other. There's no problem there. There's no inconsistencies in how we've applied Kirchhoff's current law. So those 2 equations I just wrote down there could be rearranged in this way. And of course, I could give you some values of R1 and R2 and the current sources, and then ask you to solve for V1 and V2. And that's just then solving simultaneous equations, which is you've got to do to solve for them, but it's not really what we're focused on, which is the actual circuit analysis. So if you're reasonably comfortable with that, then I'll do a quick review of digital systems for you. Which is another, people with too much time on their hands. Not sure if you've seen this, but teach you all about AND gates and OR gates and so on. One output one, one input one, output one, and the other. There you go. One input one isn't enough. You need both. So what's an XOR gate? Exactly one of the inputs 1 produces a 1, but not both. It is called people with too much time on their hands. No, it doesn't. That works. Fast forward, it's alright. Both of them 1 at the same time. Output 0. Look at that. Creative genius. So there's your quick review of digital logic. So here's a bigger circuit. It's got 3 nodes. 3 nodes. But conceptually it is no more difficult than the one with 2 nodes, or the one with, if you've got it, you've got it. And it's not going to matter how many nodes the circuit has. You're just repeating the same technique. It's why you can write a computer program to solve circuits using this technique. It is systematic. You don't have to wait for divine inspiration to determine how to solve the circuit. Let's see if we can do it for node 1 in this example. Node 1. This one here. Now it's a bit of a sort of funny distributed node because it's all of this. So I've got 4 currents to add up. I have this one. What's that? What's that current down there? B1 on R1. Excellent. I've got this current. What's that? V1 minus whatever's over here, V3 divided by R3. Plus, I've got this one. What's that? V1 minus V2 on R2. And I've got this one, which is minus IA, equals 0. Therefore, if I simplify that, I'll see it's 1 on R1 plus 1 on R2, on R, yeah, that'll do, that's right, plus 1 on R3 times V1 minus 1 on R2 V2 minus 1 on R3 V3, there's the V3, it's got a minus 1 on R3 outside it, equals IA. So that is an equation 1, Kirchhoff's current law at node 1. In terms of the unknowns V1, V2 and V3, I'm assuming all the resistor values and the independent current sources are actually knowns. They're given to me. They're parameters, the things I'm trying to solve for, V1, V2 and V3. So if you could do that one, then I'm hoping you can do node 2 yourselves, and that'll be the third melts question. So I'll just get out of that. KCL at node 2 gives in terms of V1, V2 and V3. So there's your task. Which of those equations? Oh, someone's jumped on there early. So see how you go. I'll just blank that out for a sec. I'm doing Kirchhoff's current law at node 2 in terms of V1, V2 and V3. Not in terms of the currents. I don't want to introduce more unknowns. I just want my 3 unknowns, V1, V2 and V3. Everything in terms of those. Well, I mean, you can use currents IA and IB, but not the I5, I1, I2, I3, I4, I5. That current plus that current plus that current. 3 currents to add in this particular example. Feel free to chat, make noise, chat amongst yourselves. Should we have a look? A lot of answers already. Whoa. All right. That's pretty solid. Looks pretty good. So a whole lot of people said C. Let's just double check it. We should have this current is V2 minus V1 on R2 plus V2 on R4, that's the one down there, plus this one, which is V2 minus V3 on R5 equals 0. That's the C. 75 out of 79 responses had that. It's, to me, a fairly good indication that you know what's going on here. Or you just guess, your good guesses could be it as well. There's one more to do. At node 3, I have that current, which is V3 minus V, the one back over here, which was V1 on R3, plus this one, which is V3 minus V2 on R5, plus that one, which is IB equals 0. You could simplify that, minus 1 on R3 V1, minus 1 on R5 V2, plus 1 on R3 plus 1 on R5 V3 equals 0. That would be our third equation in the 3 unknowns. Is that one all right? There they all are, grouped together. You could, in fact, solve that symbolically. You could solve for the V1, V2 and V3 in terms of all the parameters, or I could give you the values of R1, R2, R3, R4, R5, IA and IB and ask you to solve those 3 simultaneous equations in 3 unknowns. You might have to do 3 in an exam, probably not 4. I don't usually like to ask more than about 2 in an exam. More interested in, can you write down all the equations? Then there's a bit of maths to work out what the actual voltages are. When you've got those voltages, V1, V2 and V3, it should be that any other current or voltage in the circuit can be written quite simply in terms of those 3 voltages. So it looks like you had the hang of that. The only thing we have to worry about now is what happens, and given that it's fairly good timing, what would we do if this, instead of being a current source, was a voltage source? 7 volts plus minus 7 volts. What is the equation that I write down for node 1? If that was a 7 volt voltage source there, what is the equation I write down for node 1? I want to do Kirchhoff's current law at that node, do I? Well, the problem is I don't know what that current is. I can't write that current in terms of the node voltages anymore. So what am I going to do? What equation do I write down for node 1? Let's back up a little bit and think, what are we trying to find? We're trying to find V1, V2 and V3. Well, what's V1? 7 volts. So in fact, that's it. I just write down V1 equals 7 volts. That is my equation. So it's not harder, it's in fact easier if I've got one of those voltage sources. But if you blindly tried to apply KCL at every node again, then it wouldn't work. And so that's one trick to worry about. If there's a voltage source between ground and one of your nodes, you can immediately write down the value, the voltage of that node. You've already solved it. All right, that's great, that's good. We're doing next lecture now. I'll finish that. What if there was a voltage source here, plus minus 4 volts? So it's not between ground and a node, it's between two other nodes. There's a voltage source up there. What do I do now? Can you immediately give me an equation that relates two of the voltages in the circuit? Yep. V1 minus V3 equals 4 volts. Excellent. Remember, this was V1 here. From there, this is V3. So V1 minus V3 must be 4 volts. There's one of my equations. There's one then slight trick. We've still got to apply Kirchhoff's current laws. And for that, we're going to apply it at something called a supernode. Not just at a node, but a supernode. That's going to have to wait till the next lecture. So, that's all we have to do. You've got your nodal analysis. But how do we deal with voltage sources when they're in there? But we're nearly there, in fact. So that's what we'll do next lecture. Dependent sources and voltage sources, we'll put them into the mix. But then, any circuit, systematically, you can analyse it. See you on Wednesday.